Okay. Hello everyone. Today we introduce CCNA3, the first module, single area OSPF version 2 concepts. Right. From the last course, CCNA2, the last chapters, we touched on routing. We touched on routing concepts. We introduced routing and we mentioned two main functions: path determination and packet forwarding. We discussed ways of how that is done, one which is manually and the other one which is dynamically. So we discussed IP static routing. We got done with that one. And for dynamic, I think we just introduced the basics, but we didn't touch on specific protocols which dynamically allows routers to perform their duties. So with this one, we start with single area OSPF, which is open shortest path first. Version 2, that's not a huge issue. Version 2 is just OSPF for IPv4 networks, and we have version 3, which is for IPv6 networks. So this is what we are going to be touching on. All right. The module objective is to explain how single area OSPF operates in both point-to-point and broadcast multi-access networks. So we'll describe the basic OSPF features, characteristics, and the packet types used in the single area OSPF. And lastly, we'll explain how single area OSPF operates. So basically, this is the first chapter, the first module, just going through the concepts. The second one, we'll actually do the configurations for OSPF version 2. Right. Features and characteristics. So OSPF is a link state routing protocol developed to be an alternative for distance vector protocols such as RIP. Starting there, when we introduced the type of protocols that we have, those are the two main types that we introduced: link state and distance vector. And what do we mean by that? Starting with distance vector. So with the distance vector, we have routers only sharing information with their neighbors and only that. So in a network, let's say we have a network, can I draw something? All right. All right, so let's say we are in a network, we have three routers, all right, R1, R2, and R3. With the distance vector protocols like RIP, we have R1 only sharing information with R2. Any updates in network changes, it only shares with R2. Then R2 shares with R3. Then R2 shares with R3. So there's only communication between these two, and there is communication between these two. If not directly connected, if there is no direct connection between R1 and R3, there will be no direct communication between the two. That is distance vector for you. With the link state, it's very important to understand the difference between these two. With the link state, we have the router sharing protocol, sharing routing information with every router in the network. So in this example, actually what R1 does when it shares its information, it broadcasts, a multicast actually, right? There is a multicast for enabled routers. That multicast is shared with every router in the network that is enabled. So instead of having only one, forming only adjacents with one router, this R1 communicates with R2 via multicast, communicates with R3 via multicast. The same with R2, it communicates with these two via multicast. That is link state. The advantages, most important thing to note is the advantages that come with having link state protocols. So with the link state protocols, when you talk of convergence now, say something happens in the network, you already have your routing table, routing is already being performed, a link gets down, it means that route needs to be removed from the routing table. Convergence is that time between when there is a change and when that change, the network reconfigures itself to accommodate that change. So if you are using RIP, a distance vector, it will take more time for convergence because R1, the router is only communicating with its neighbor only, directly connected neighbor. It takes more time. So R1 communicates with R2 that something has happened, something has changed. Then R2 takes that information, communicates with R3 in a network with 20, 30 routers. It takes a lot of time. But with link state, a multicast is sent at once. Could we have a change in the network? So a multicast is sent to every router. We have a change in the network. Every router receives that information, processes. If it is to change its LSTP, well, let's say its topology table or routing table, then it is made in less time. So that is one of the advantages of my link state protocols over my distance vector protocols. Right. So OSPF has a significant advantage of RIP that it offers fast convergence and scales to much larger network implementations. Right. We've talked about fast convergence. Now, in terms of scalability, it's evident. Instead of sending protocols one route after the other, it's very difficult in a network yakakurisa stereki. To expand your network is very difficult because one router needs to talk to another and another, etc. But with the link state, if you add a router in the network, that's a change. When the network reconfigures itself, a multicast is sent to every router, including router or header. Therefore, it's easier to scale in a larger network environments using link state uh, rather than using RIP, which is a distance, rather than using distance vector protocols. Right, a link state is an interface on a router. A link is an interface on a router, a network segment that connects two routers on a stub network or on Ethernet LAN. So we know what a link is. This is a link, a connection between it might be, let's just say, two devices. It can be an end device and a router. But in this case, we're focusing on routers. This is basically a link, a connection, all right? Information about the state of a link is known as a link state, all right? The information about availability of this link, cost. We mentioned here cost, patakataura among protocols. Could we use cost to determine what is the best path to use in a network? So all that information, do I run the link state? Could ID, my router IDs, router priority, information about the link, right? In doing the link state, we see link state quite often in this module. All right, this module covers basic single area OSPF implementations and configurations. All right, I'll touch with CCNA, we don't deal with multi-area OSPF. All right, I'll touch briefly on that. Probably to pop up Kumberi, but let me just touch on that. The difference between single area OSPF and multi-area OSPF. Right, with single area OSPF, it's like we are dealing with one network, one small network. It's the same thing as dealing with one subnet, if I can put it like that. It's the same thing with dealing with one VLAN, right? The same concepts we have with IP subnetting, VLANs, the concepts of segmentation. One huge network being segmented into smaller networks is almost the same thing with OSPF. Now with multi-area OSPF, we have one large network, right? Then we have smaller networks. That one large network is divided, is segmented into smaller networks so that my routing information is shared within only that small area. Some advantages, it is advantages which comes with that, which we are going to discuss. So routing information, it is only propagated in a single area. Then can I consider the whole network as a whole? These areas start sharing network, they start sharing their routing information using one router, the border router. So instead of having one large network, we break down the network into smaller areas. In those smaller areas, they constitute what we call a multi-area OSPF. So when we are now integrating all the single area OSPF, this is a single area, right? Only one area. This is single area OSPF. That is what we will focus on, that one single area. But with multi-area, there is now exchange of information between all the areas in the network, which we are not going to be touching on, but only deal with single area OSPF, right? But main thing to understand the difference between single area and multi-area, start with understanding segmentation IP network with subnetting. Start with understanding surveillance as well. We have one large network. Communication in one large network is very difficult. It needs to be segmented into very smaller parts. Those smaller parts, they communicate in their own. Then information can went outside. It then goes out. That's basically single area and multi-area. All right, slide 5, components of OSPF. Right, here we discuss how the routers know about routes in their area in this slide. So all routing protocols share similar components. They all use routing protocols of this. They all use routing protocol messages to exchange route information. The message helps build data structures which are then processed using a routing organ or routing algorithm. Right? How does my routers know my routes which exist in the network in the app? With IP static routing, with static routing, manual configuration, you actually have to configure kuudza router kuti kune network yakati iri kwakati. That is manual configuration. But with dynamic, you don't have to do that. So how does the routers know kuti my networks that exist within your network in the app? So we have my protocol messages, routing protocol messages anoshandiswa to exchange information nekuudzana kuti kwakati kune route or hakuna. Right, my messages iwayo, we have the hello packet, the database description packet, link state request packet, link state update, and the link state acknowledgement packet. We discuss all those in brief. The idea to get here is there are messages being exchanged. When we started CCNA 1, what is a protocol? A protocol is a rule that governs how messages are being exchanged in a network. So exchange of information, DOMA protocols, information exchange, we have the hello packet, that's the information. We have the DBD, the database description, the LSA, the LSR, and the LS. So this is the LSU, this is the LSR request, database description. This is just the hello packet. And the last one, this is the link state acknowledgement, ACK. Those are the packets which are exchanged. Ndoinokuudza kuti kwakati kune network. Ndoinoudza router kwakati kune network yakati. We discuss those pamberi bijana. Right, let's go. Slide 6. Types of OSPF packets. Right. So my packets are true, as I mentioned in the previous slide, which are used to exchange information. We have the hello, which discovers neighbors and builds adjacency between them. Right, so with the hello packet, a router sends and listens for the hello packets. Why? To form what we call adjacency. Right, with adjacency, this is basically establishing communication between two routers. It's like when two people meet. How are you? Neighbor, hello, how are you? It's the same thing. Pamunosangana ngotange nekutaura nyaya direct kuti inini ndinobva kwakati, ndinoziva ani. You start with the hello, how are you? Mumwe munhu respond. Akasaresponda, zviro kuti asinotaura newe. It's the same thing with my routers. So hello packets, they are sent to discover neighbors and build adjacencies between them. So between two marouters, hello packet rinosendwa, uye akaresponda kuti bo zviri sei, how are you, then we have formed an adjacency. Then we can start sharing information kuti inini ndinonzi ani, zvandinoziva marauta ndoziva ndeapi. So the starting point is the hello packet. Router number 2 ikataura rikasaresponda to that hello packet, pakasava neresponse, router number 2 doesn't want to communicate with router number 1. Therefore, there will be no information which will be shared. There is no adjacency formed between those two routers. Right, with the database description, DBD, it checks for database synchronization between the routers. Right, adjacent routers tell each other the networks they know. So with the database description, this is where we start sharing information. By hello apa, pamaita initial communication, hello, how are you, I think that's good enough for the hello packet. All that information is there. Then after that exchange, you go up a next step. I'm not share my DBD. So my DBD, you're actually sharing with inini is router number 1. Ndinoziva network yakati. And router number 1 inoziva directly connected networks. That's a fact. Right, and we got 2 routers, let's say 3. By default, we got 3 routers here. Right, let's do this. By default, R1 knows network irabai because it's directly connected to that. R2 also knows that network. R3 does not know this network because it's not directly connected to that. In static configuration, pa R1 we configured kuti R1 kune network iri uku ishi, irapa ishi. Taiudza R1 kuti kune network iriko. With my dynamic routing protocols, information inoshayiwa ndeyekungoti inini as R1 ndinoziva network irapa. Over senda DBD kuna R2 nani na R3. R3 kana akuda kusenda information ku network iri apa, akutoiziva because R1 is actually had sent a DBD kuti amunzoti inini ndinoziva network yakati. Saka iyi kana ida kusendera network iri apa inongosendera probably to R1, then R1 yozoti network ichasendera sei network yayo. Basically that is it with DBDs. So a router, it shares my networks ainoziva by default, which are obviously the directly connected networks. Those are DBDs. Now kana my DBDs ashayiwa, let's say my routers asashare kuti ini ndinozivani, then we have a case yekuti all my networks akuzikanwa. R1 akuziva zvese zviri kusvika kuna R3, R2 akuziva zvese R1 and R3, R3 akuziva zvese R2 and R1 because they've actually shared my DBDs. Right, with link state requests specific link state records from router to router. Right, what do we have with LSR? This is sent if a router is missing information, basically. So let's say my DBDs ashayiwa ese, but there is a change somewhere itika paederwa imwe network. Then R1 paederwa imwe router panapa R4. Alright, R1 madBDs pashayiwa R4 yanga isipo. Payaederwa R1 munhu ari PC iri panapa iri kuda kusendera kuna R4. Iri kuziva kuti kune network iriko kuna R4, but R1 actually doesn't have that information. Right, so PC1 painoda kusenda kuna R4 inosenda information through R1, yobvunza R1, youdza R1 ndoda kusenda information kwakati, but information yeR4 haimo murouting table or topology table yeR1. So R1 when it compares information yairi kunzi ita neinformation yainayo, it sees kuti hapana kwandinokwanisa kusenda packet because handina network yacho in my databases. So what does it do? Inongosenda inonzi request. So it sends a request kuma a multicast again. Inozama routers ese kuti I'm looking for this network iri papi. Then the network iyoyo it will send an update kuti panapa pane network nyowani iripo iri directly connected to R4. then update yoiswa topology table, yoiswa database. Let's use database. Yoiswa database, then PC yako is not proof and send it up. And basically, it happens like that. So in LSU, in LSR, it's a request, in LSU, it's an update. So router request out and when a router has missing information in its databases, send a request. It does not send a DBD instead. DBD is sort of my initial stages through establish adjacency yedu, establish a convergence, then convergence kana yapera nditori database kudhara ndinaro, but I have some information missing, so I just send a request, then an update comes, right? Then with link state acknowledgement, this inotangira ipapa yapa hello up makasimba here, how are you? If someone doesn't send an acknowledgement, makasimba here, that's basically acknowledgement. It's just a response. Could I send as a if you've sent an update between R1 and R2, R2 will send the update to R1, R1 sends an acknowledgement with update yashika. Let's say bo. Basically, that's an acknowledgement. Right. Then we have one more receipt app. Runs the link state LSA. Link state advertisement. Link state advertisement, let me put it this way. Link state in LSU, in update, it is made up of multiple LSAs, advertisements. So to keep it much simpler, when send a request, response the LSA, the link state advertisement. So request E1, response can R1, LSA. But my responses are multiple, update instead. So we look at LSA Pamberi. I just had to add that. Panap. Right, moving on. Let's go on slide number 7. Right, that is structure here, yellow packet. Right, the OSPF type 1 packet is the yellow packet. They are used to do the following: discover OSPF neighbors and establish neighbor. Just since we discussed that. Do I not discover who is my neighbor? Which router is my neighbor? Kana ndaziva kuti neighbor wangu ndiani, ndo establish adjacent. Makasimba here, how are you? Adjacent established, then we start sharing information. Right, the advertised parameters on which two routers must agree to become neighbors. They elect designated router and backup designated router on multi-access networks like Ethernet. We'll touch on the issue election. So pamanoisa my yellow packets, send my yellow packets. Discuss not a designated router, which is basically a router in a network not multi-access. Inobvumirwa kutaura on behalf of every other router in the network. We'll get there. So information yekuti router richaita DR nderipi, router richaita BDR nderipi, it is contained in the yellow packets. So focusing on this area here, we can see the yellow intervals. We discussed that. The dead intervals, we discussed that. The designated router, information yekuti DR and DN in this network. Who is the BDR in this network? Who are the neighbors? Who are my neighbors as a router? So all that information in the yellow packet, we'll look at all those pump it up. Right. Link state updates. LSUs are also used to forward OSPF routing updates. An LSU packet can contain 11 different types of LSAs. So that's the thing I was talking about. So an LSU is basically 11, yep, and 8 though. The other 3, I think they should be for version 3, right? Different names as well for version 3, right? So an LSU is just my LSAs akawanda, multiple LSAs. So an LSU, an update contains 11 different types of LSAs. OSPFv2 renamed several of these LSAs and also contains 2 additional LSAs. LSU and LSA are often used interchangeably, but the correct hierarchy is LSU packet contains LSA messages. Right? Let's move. Components of OSPF. right? OSPF messages are used to create and maintain 3 OSPF databases, right? This is very important. Starting with, what is a database? A database, how do I put it? It is just a data structure which is used to store information. In this case, we have 3 of them: the adjacency, we have the link state, and the forwarding database. The adjacency lists all the neighbor routers to which a router is established bidirectional communication. So after hello yapera, neighbor anobva atoederwa adjacency database. Then from the adjacency database, we have the neighbor table inotiudza kuti who is our neighbor, who is the neighbors of R1, R1 and R2. Who is the neighbors of R1? In this case, tinenge tingori R2 ndio anenge ari neighbor. Tikaisa this, after adjacency yapera, R1 anenge anodisplay in its neighbor table R1 and R2 and R3 kuti ndo maneighbors angu. And basically that's it. So it starts with understanding kuti tine adjacency database. What is that? It gives us neighbor information. Who is our neighbors after adjacency has been reached, right? With link state database, after my DBDs are exchanged, information database description exchanged, all right? The LSDB is formed, the link state database, which is the topology table. The topology table basically describes the network yes, network yes. So R3, let's look at this network, a small network. R3, that is a topology table, R3. Topology table. After my DBDs are exchanged, zvese zvaexchanged information yese, my broadcast ema yellow nema LSA aitwa ese, we are close to convergence, right? Every router yakuziva every other router in the network. In the topology table, the R3 tinenge titori R1 R2, because R3 yakutoziva kuti munetwork mune R1 R2. So that is the link state database, which lists all information about the routers in the network. This happens after my DBDs happens to exchange. So here we have my yellow packets, adjacency yapera. This is the first step. Then panapa, my DBDs are exchanged. Takuziva kuti network yese yakaita sei, which is the topology basically. Network yese yakaita sei. Right, the database represents the network link state database. All routers within an area have identical LSDBs. Why they have identical? Right, because they know every other router in the network. R1, let's just say, minimum topology table, let's include R3 as well. Because R3 aruziva my neighbors, aruziva my networks are directly connected to. R1 itself, R2 and R3, this is the topology table. So you see the information in topology table is the same for every router in the network, which is not the same for my adjacency. Per adjacency, R1 anenge arongoziva R2 and R3 ndo adjacency yake. Then R3 arikuziva R1 chete, which is different. R2 arikuziva R1 chete. R3 arikuziva R1, R2 arikuziva R1. So these two are different already. So LSDB is not unique. It's the same for every router. It's just information that my routers ASR network the app. Adjacency database is a bit different. It's unique for a given router because it's talking about what my neighbors are on the app chat. Right. Then tabva exchange yema DBDs takuziva kuti network yedu yese yakaita sei, tamepa network yedu yese takuziva kuti yakaita sei. We have now the algorithm, shortest path first, the SPF algorithm. It takes over now. Rakuziva kuti network yese yakamira sei, topology yese yakuziva. Yakuchitanga kushandisa information yanga muri kushare, for example, my cost. Algorithm yakutanga kushandisa my cost to calculate what is the best route from a given router to another destination network. Information yanenge yawana kuti best route ndeipi ndo inenge iri muforwarding database ichistowewa routing table. So the forwarding database, it lists It's a list of routes generated when an algorithm is run on the link state database. Each router's routing table is unique and contains information on how and where to send packets to other routers. Can be viewed using show IP route command. We'll get there. Right, so these are the three types of databases that we have: adjacency, link state, forwarding, in their respective tables, the neighbor, the topology, and the routing. You need to understand the difference between these three. Typical exam questions, inokupa a description of one of any of the three arapa. Yokudza kuti chii ichochi, i-adjacency here, LSDB here kana kuti forwarding. So you need to know kuti zvizvozvo. Right. Link state operation. To maintain routing information, OSPF routers complete a generic link state routing process to reach a state of convergence. The following are the link state routing steps that are completed. Right, we have step number 1, establishing neighbor adjacency, exchange link state advertisements, build the LSDB, execute the SPF algorithm, choose the best route. So I think I've already touched on all these steps. Now putting them into a bit more perspective, number 1, establishing neighbor adjacency. Ndo step yekutanga yatataura nezvayo yema-yellow packets. So this is where my yellow packets are being exchanged. Routers recognize each other before they can share information. That is step number 1. Step number 2, exchange LSAs. Right, after adjacency is established, the LSAs are exchanged. In my LSAs, they contain information, your cost, or a state, let's just say link state. My LSAs, they contain link state information, which includes nyaya cost about the directly connected links. Right, routers flood their LSAs to adjacent neighbors until all routers in the network have LSAs. So this is just exchange yema LSAs in the second step. Takuziva after adjacency, takuziva who is my neighbor, then we start exchanging information. But no exchange information, my LSAs. When every other router receive my LSAs, it responds in an hour. Then we've created a database redo. That's how we build step number 3. That's how we build the link state database. All right. All LSAs are received. Routers start building their topology table. So it's step number 3. Ndoparutanga ku build a topology table. My LSAs, information about my link states yashayiwa. Here, apa tina adjacency database, ni neighbor table, step number 1, right? Step number 3, topology tables. Then after my topology tables, takuziva network yese, the algorithm takes over, right? We execute the algorithm. You shandisa information engari muma LSAs. Ye cost, for example, specifically cost. Could the best route to a destination network in the EP. Can I have best route to a destination route routing table? Right, and basically these are the steps which are used to reach a state of convergence. Can I answer better than convergence? Now, can I send a packet rako? Tunongenotarisa routing table. Route racho ichi todaenda destination network yakati, the best route rekushandisa ichi ndorinenge riri routing table, then information yako forward to the destination network. Right. Single area and multi-area OSPF. I've touched on this. To make OSPF more efficient and scalable, OSPF supports hierarchical routing using areas. You see IP by definition, it also used levels a hierarchy as well, right? An OSPF area is a group of routers that share the same link database information in their LSDBs. OSPF can be implemented in one of the two ways, single area and multi-area. The focus of this module is on single area OSPF. All right. All areas must connect to the backbone, area 0. All routers are in one area. Best practice is to use area 0. Right, with Single area OSPF. When we talk of the area, permanent configurations, there is a description yekuti router riri area ipi. So when we are talking of single area OSPF, every router, this is the best practice. You use area 0, right? Area 0 forms the backbone of the network. Now kana one among my areas akawanda, let's say you have area 1, zvinoita kuti mamauti area OSPF. Then area number 2, you will see that all of the areas, they should be somehow connected to the backbone. We are not going to discuss much about area, but just giving an idea of what area I gotta say. So in area 0, there is exchange between my routers are in area 0. You see with LSDB information yakafanana because it was my routers ASR in this network. Hatikuziva ku area kuno. Right? Now kana taunoziva ku area ish. There is an exchange in a border router. Let's say this is our border router. It exchanges information in a border router in area muno. Yours are all the information about area Inoi. Yours are all information about area 1. And basically, information is there, is shared all over the network until a state of convergency, then toshitanga routing it. Right. Seeing I have less than 1 minute, let me stop this one so that we can continue in the next session. Then the matter is not dura.